So my name is Gordon Cooper. I'm one of the product marketing managers here at NXP. I'm responsible for some of our high-end micros, and I have with me
Xianghui Wang. I came from the applications team. I hope to support your application in the future.
Okay, so what we're going to talk about today is how do you add USB to your system. We're going to talk about using our LPC11U as an example. So the U is for USB. It's a low-end Cortex M0 microcontroller with USB device capabilities. So we're going to use that hopefully to kind of walk you through the steps of how would you add USB into an embedded design. So you don't have to be an expert. We try to make it easy for you. You don't have to have a lot of USB experience. And if you need a micro with basic USB connectivity and some other connectivity, we'll talk about why the 11U6x might be a good fit. But there are other members of our family that might be a better fit for what you need. So the goal of the session is the end is you have an overview of USB and the steps you needed to add it into an embedded system. So for our overview, for those of you who aren't USB experts, we're going to give you a very, very quick overview of what USB is and connectivity and some things you might need to know. Then we'll talk about some selection choices as you choose a processor, host, device, full speed, high speed, some of those considerations. And then for those of you who have more of a hardware design background, we'll talk about some things that we do to make it easier for you as a hardware designer. If you're more of a software design, we'll talk about the software design considerations you need. And then if you have a USB design, if you're making a product with USB, you probably want to productize and certify your design so you can have the little USB logo. So we'll talk about a couple of things that you need to know there. Right? That's our agenda for the day. So now a USB overview. Let me turn it over to Xianghui.
Sure. So I think since you're here, you must be interested in USB. So do you need USB? What USB modes are you considering? You wanted to do host, device, or the OTG? Some other considerations are whether you wanted to have your USB system as bus-powered or self-powered. How much power do you need to drive if you're a host? Some basic technology on the USB side, what transfer speed do you need? Nowadays, we have super speed, high speed, full speed, and low speed USB systems. Today, our focus is full speed and low speed. NXP does provide parts that supports high speed. Another thing to consider in the transfer domain is what class you're using. These classes will determine what transfer speed and what transfer type you're using. We have human interface device, mass storage class, communication device class, composite audio, or some vendor specific. These classes and transfer types also determine how many endpoints you will need for the system. And finally, are you planning to use a USB for field firmware upgrade? And that we can provide this capability with the DFU class. USB is everywhere nowadays. Certainly it's because of these key features. It's hot swappable, plug and play, high performance in terms of data transfer. Compared with I2C, SPI, and UART, USB is transferring at a much higher speed. And this also brings us to the attention nowadays USB can provide a bridging solution to some legacy serial port, especially with the device we're talking about today, the 11U6x, because it gets a lot of serial ports on it and a very easy to use USB solution. USB is a star-tiered bus topology which can connect to a maximum 127 devices from the host, so it's very expandable. Of course, USB is ubiquitous, it's everywhere, so let's discuss some details on the USB. Today, our focus is USB 2.0. USB 2.0 covers 3 speed, low speed at 1.5 megabit per second, full speed at 12 megabit per second, and high speed at 480 megabit per second. The physical side, USB is a 4-wire serial bus with V bus and ground, and as well as the twist D plus and D minus for differential signal transmission. Some of the basics on the connector side we have provided here. On the host side, we have A receptacle. On the device side, we have connector B receptacle, and there are many variants to the B. On the top right is the most common B receptacle, and we also have mini B and macro B. These two connectors added a fifth pin that is mainly to accommodate the on-the-go device. So one of the first things when we think about USB applications is that we need to choose what class do we use for the USB systems. Here we have listed a couple common USB classes. CDC stands for Communication Device Class. It's mainly to enumerate the USB as a virtual COM port. Many of us has used FTDI cable, which basically goes from your USB to the PC and appear as a virtual COM port. Mass storage class, we all use a USB stick. HID class, human interface device, like our keyboard, our mouse. These are communicating with a human and use interrupt-driven transfer for the human interface device class. Audio class and printer class, these are some of the common classes we have seen. Implemented using certain transfer types. Control transfer is required for all USB devices. The first communication between the host and device is to use control transfer to enumerate the device. Bulk transfer is used for guaranteed delivery, but it doesn't have guaranteed bandwidth. It will use whatever left from the PC after allocating to interrupt and isochronous transfer. So interrupt transfer is a guaranteed delivery with periodic requirement from the device. Like for example, normally people use the interrupt transfer for the HID device because you want a PC to periodically see if there is input from the user. Isochronous transfer is a guaranteed bandwidth so that information can be delivered as soon as possible, which is mostly used for video audio devices where latency is not allowed. However, isochronous transfer doesn't have error tracking. Like you drop a little bit of the video or sound, but the purpose is to catch up the speed. So we already talked a little bit about enumeration in the previous slides. So here we will go through some of the topics we touched just now to know a bit detailed information on the USB systems. So enumeration is much like any enumeration. It's basically to let the device know, I'm here, here is my feature, and to let the host know the device's feature, and the host will assign an address to the device and carry on the following communication. It's a programmable process. In NXP's case, much of this enumeration process is covered by our drivers. Many devices has on-chip ROM driver, which help us to handle this enumeration process. Once the host knows the device is here, the host will reset the device and assign the address to the device, and the device will return its vendor ID, part ID, power consumption, and transfer type, transfer package size, all of those information to the host, so the host know how to carry on the communication following. The descriptor basically is what the device returns to the host to identify itself's capabilities. we already mentioned it includes power consumption, VID, PID information, USB specification, transfer types, what class the devices are, and packet size.
So this is the handshake process between the host and the device, which makes plug and play possible. When you plug it in, it has to be able to say, hey, here's who I am, okay, here are your drivers, and communicate back and forth. We give you the default enumeration, so this is more background for you. The drivers take care of this. If you want to go modify it, it is programmable. You can go, change the fields. You can go do that, but you don't have to. So this is more understanding the handshake process than actually having to program it yourselves.
So some of you already asked about endpoint. So here, this diagram will show us exactly how the transfer happens. And this applies to the enumeration process as well. So these elements are all the basic elements that happens during a USB transfer, USB transaction. So if we look at the host side, when the host wants to transfer something to the device, it thinks it got some paths going from the host to the device. If we look at this diagram, the 0 and 1 can represent two individual paths that goes from the host to the device. Each individual 0 or 1 block is in fact a packet. The packet doesn't have to be sequential on the different paths. It depends on the priority. Each packet has three fields: the sync field, database, and end of packet. Between these packets are the idle period. When we talk about the USB idle, between these packets, there is idle period. In this case, we have the endpoint 0 here. Endpoint 0 is a default control endpoint. So for any USB communication, this is a must-have endpoint. Normally, devices has couple endpoints. In our case, the 11U6x has 5 endpoints, 5 logical endpoints, 10 physical endpoints. Each endpoint have an in endpoint and an out endpoint. The in and out is looking from the host perspective. If the host sends something out to the device, that's using the device's out endpoint. If the device returns something to the host, it's using the device's in endpoint.
And an endpoint is a buffer.
The endpoint on the device side, in most cases, are implemented using buffers. You can think in this way. When the device wants to send something out, it writes to its out buffer. That is targeting to its out endpoint. When the host sends something to the device receives it from the in endpoint, which land in the in buffer. It's very easy to understand in this way. So now we know the basics of USB systems. We will go into how do we select a device.
Yeah, do you want me to go through this?
Yes,
Yeah.
Gordon will go through the slides with you.
So you might say, hey, I want to build a device, a mouse as an example. Full speed is plenty of speed. You don't need high speed for a mouse. What would you need high speed for? Well, even audio, full speed is probably enough if you're doing stereo, 2-channel. If you're doing multi-channel audio, or you're sending data that you need a really high speed, then you can look at the high-speed PHY. And we do see if you're sending a lot of data quickly, that we do see customers really like that. So you have a couple choices. Am I host or am I device? I'm device typically if I'm connecting to the PC. But I might be host if I want to plug a memory stick in or I have some other connectivity. So here on our sort of chart of micros, these are all NXP micros. If it starts with an LPC, that's our convention for it's one of our microcontrollers. On the 11U, it's a Cortex M0 running at 50 megahertz. You have low speed, full speed, and we're device only, and with drivers and ROM. That's what this is. So a mouse or other sort of device connectivity. I mentioned mouse because there's a lot of gaming mouse built around this, typically in Taiwan and some of the other areas. We have a lot of design wins for that. If you want host capability, you might want to look at our 1700 or 4000 here. It can be host or device. You can actually have both if you want available. So in the interest of kind of educating you guys, we'll spend some time on the device side. Okay, so choosing a micro, how do we make it easier for you if you choose the micro? Well, one of the things we do is we certify it. So if the part is certified, it makes it easier for you to certify your product, your end product, which then gives you all the little USB logos you can put on your product. So we certify it. We have certified drivers. We have a lot of development boards with board support packages. We have free software, which we'll talk about. And I mentioned the device drivers in ROM. Now, we don't have all of them. We have the most common ones. I think we have 4 of them in ROM, which we'll talk about. We have software drivers you can download from our websites. So if we don't have it in ROM, we might have it available, and there's some third parties that also have drivers available. I mentioned the on-chip PHY, so again, you only have to worry about the 4 pins. You don't have to worry about connecting an external chip to get the PHY. If you decide you want device, so it narrows it down, maybe we'll look at our 11U family. There's multiple members of the family, so we actually give in the very low end 11U10. So from a price point, this is lower memory. And really, memory drives our cost because it increases the die size. If there's any one thing we put on our chip, it's the memory that increases the cost. So the 11U10X is 32K of flash and 6K of SRAM. It doesn't have ROM drivers, but the 20 has the ROM drivers built in, but you can certainly just run out of software. The advantage of ROM drivers in a smaller flash size is you don't have to waste any flash size. You don't have to give up 6K or so of flash size by having your ROM drivers. Now, when you get to a bigger chip like this with 256K flash, you got quite a bit of flash. It becomes a little less important. But this newest version of the part uses the Cortex M0 Plus. If you're familiar with M0 versus M0 Plus, not a significant difference, code compatible, but it's 2-stage pipeline instead of 3, a little bit better on the power consumption. We've added a lot of connectivity as well, so you can see we've gone to higher UARTs, more SPI, larger flash, faster ADC, and some extra options there that you don't have on some of these. Now, only valuable if you need them. So we give you a spectrum of choices here. This is the part that you'll have on this board. Here's the block diagram, and I won't go into it in detail other than to say, certainly here's the USB with PHY, the key feature for you, but you have your standard SPI, I2C, UART or USART in this case, connectivity, timers, all the things you'd expect in a micro, flash, EEPROM, etc., ADC, temp sensor. Our standard development platform was the Espresso, which was a kind of a long, thin board. We've moved to the Espresso version 2, so you get the version 2. So there's some Arduino Shield connectors. Here's USB to plug in. If you download our software, if you need your development tools, we have a free version of tools up to 256K of flash. This happens to have 256K of flash, so you can actually download tools and be all set. So what you really need is this board, a USB cable, and a free download, and you're up and running. So in fact, you're in good shape because we already have the debug capability built onto this board. So all you really need is the cable and the software download to get started. Okay, if you're more on the hardware side, here are some considerations for you from a hardware side. One of the first things you want is give me some reference schematics. So
on this board, we have this device 11U6x. It's a 100-pin package. For the USB connection, you just need to connect D+, D- to the macro B connector that is on the board. And provide external crystal for USB operation. For USB operation, you need external crystal for full speed and high speed operation. So, looks very simple, right? So here we summarize what are the hardware features that can make the USB design easier on this part. So we have on-chip PHY, and in addition, for full speed operation, for all of the other parts, we need the termination resistor of 45 ohm. For NXP part, we provide 33 ohm external termination resistor for operation in full speed. However, for this particular family, we have the 33 ohm termination resistor built on chip, both D plus and D minus line. So that's why in the previous schematic, we do not need termination resistors on the D plus and D minus. Also, NXP has a soft connect feature that basically means you can use your software to control when do you want to connect to the host. Connecting to the host in the USB world is by pulling up on the D plus or the D minus line. In terms of the full speed operation, we need to pull up on the D plus line. For this family, the pull-up resistor is also inside the chip, so you don't need this resistor outside in the schematic as well. Some other features on NXP's USB part are integrated DMA. So you can leverage the DMA performance to save the CPU bandwidth. And we have double buffering to boost the bulk and isochronous transfer. All NXP CPU parts support suspend, resume, and remote wake up for better power management. USB system is a device managed system in terms of power consumption. Once the host agrees with certain power, it's the device's responsibility to suspend if it sees no activity on the USB bus for 3 milliseconds. It has to drop down to a suspend mode where it consumes much less power from the host. This is especially important for bus-powered system. Normally, a full-speed and low-speed USB device consumes 100 milliampere as a unit load. But in suspend mode, it has to consume 500 microampere or less. So here is our Xtal-less low-speed USB feature. Basically, we use internal IRC to feed the USB PHY, bump up to 48 MHz, and then divide down to get the 6 MHz for the low-speed operation. Notice that for the pull-up on the low-speed operation, we need the 1.5 kilo ohm pull-up on the D- line. Here is a cross to show that the pull-up is on the D- line. So we also provide some guidelines for the USB signal routing, which you can get from the link below. We talked about how the hardware makes the system design easier. Now we would like to introduce the USB software from NXP, which helps the user to design the USB application. And we also support many middleware like the graphics, Ethernet, lateral IP. So many middleware are available free for download from our website. The chip level device and the board level packages are available in the LPC Open platform, which allows you to quickly bring up your sample project and prototyping. So here, Gordon talked about the LPC Espresso already. So it's free 250K byte download and debug, which is the largest as far as I know. I used many tools. And if you want the pro version, it's $495 license fee. For software support, we have the LPC Open LPC Open platform, which provides host stack and examples, extensive free download example code. On the right, I've listed some sample projects that is available for this part. We will provide a link later for you to download. So here we talked about some details on the ROM driver. On the ROM driver, we support HID, MSC, DFU, device field upgrade. DFU stands for device field upgrade. Basically, the device will enumerate as a mass storage on the PC as a drive. which then you can see there's a binary there. You can change that to whatever binary you want, and you already updated the device. It's very convenient and simple operation. And the CDC class. Certainly you can build custom class based on our low-level drivers.
USB used to be very specific for the consumer computing space. We're seeing many more examples where it's starting to go into the industrial space because you can, with a thumb drive or just connect your PC, now you can calibrate or update your firmware very easily, and so that's a nice feature to have the DFU capability. So no matter what your design is, you can use USB as a way to update your firmware along the way.
Okay. So with this particular device, we considered it's a good application for bridging to legacy serial devices. On this part, we have 5 users, 2 SPAI and 2 I2C bus. And plus the easy-to-use USB, we thought it's a great tool to bridge to the I2C UART and SPI devices customers currently have, especially in the industry space. These are very popular serial ports, but if they want to consider to upgrade to USB, and this device will fit in right there. And we already talked about the double buffering and the DMA driven for the USB communication. So the previous bridging solution is enabled by NXP's USB Serial I/O library. On the PC side, that's your application, where you wrote code as if you're talking to an I2C device instead of talking to USB or talking to the PC's operating system. The USB SIO library will automatically translate your I2C request to USB HID request and send to the device. This is like our 11U6 here. And on the device, it will receive through the HID USB bus and translate the HID command back to the I2C command to forward to the devices connected on the I2C bus. We will show a quick demo here that shows the USB to I2C bridge. For this entire demo, it's available download from this page, and certainly you can download the free LPC Expresso IDE to support the development. We also support CAL and IAR for this solution. So all that we need to do is download these 2 packages, build the firmware, and run the GUI. The GUI is also supported online.
So this is just an example of some of the code that you can find available. We haven't mentioned it, I think we'll do it at the end. There's a website, nxp.com is where you'd go for our data sheets and all our basic information. We actually have a second website called lpcware.com, and we'll mention it here, but that's our user site, our engineer-to-engineer site. All the code, all the downloads are available there. So this is just an example of what's available. If you go to that site, you can download this demo, run it on your board if you choose to.
Okay, we already talked about this. On the PC side, this library translates I2C to HID calls. And on the device side, the device translates the HID to I2C calls. Here we give an example. The device basically is looping through to get the command from the PC, and look what command is this. If it's trying to initialize a I2C port, then it will call the low-level driver, which is available in the sample code. So lastly, we're going to talk about productizing your USB.
We've talked about hardware design tips, we've talked about software, and again, we make it hopefully fairly easy for you. You just go download, run it on the board that you have. All you're missing is the USB cable. Now we'll talk about if you want to productize your design, you want to add USB. Basically, if you go to this lpcware.com site, we actually have a whole certification package with all the information you need. Basically, that's one kind of stop shopping, which is the hardware, schematics, software references, etc., to get you started. Are you going to show the demo? Or?
Yeah, I'm going to show it very briefly.
Okay.
This demo is basically enumerating this device as a HID device on the PC And the PC has a GUI that can talk to the USB Serial library, then the Windows HID driver to control some LED on the baseboard. There is LED, I2C LED expander controller, also from NXP, that is on the baseboard, which is controlled by the I2C port on the device we're talking about today. So this is the LPC Expresso IDE we talked about, and it's free for download at lpcware.com. So you can control the LED through the PWM on the PC. So basically the PC sends this command over through USB to the device, and the device will then translate those commands to I2C command to the I2C LED controller on the board. You can turn on and off these LEDs, but I can show you after the presentation. That's basically the idea of the USB to I2C bridging. So USB IF certification program enable measurement of compliance in real products. We have certified our device through USB IF, and you can follow the certification process we have done and to certify your product, so it's enable you to bring the device to market quickly and more compatible with the host over there. So the USB IF certification program is a matter of acceptability to meet the USB specification. Products that pass this test and on the integrator list and execute the USB IF trademark license. These three conditions guarantees and warrant the vendor to bear the USB IF logo, which are the different USB IF logos. For this case, were the basic level, full speed and low speed certified USB products. So these are the tests we have to pass to get the USB IF certification programs. A lot electrical tests, basically all the I diagram, inrush current, signal jitter are tested with this certification program. Interoperability test, we have to be able to communicate with all kinds of the USB host controller. Here we have this diagram that shows how the interoperability tests are performed. And functional tests, we have to enumerate properly. And also on the electrical side, the V bus line, D plus, D minus, never wanted to give voltage back to the host. That's what it means. So the maximum you can have there is 400 millivolt at any time when there is before and after enumeration, the V bus, D plus, D minus line cannot present to the host more than 400 millivolt. Part of the requirement is also the peripheral checklist that is required to enter the USB IF certification program. So we have provided this information at lpcware.com, including the certification package, as well as USB to I2C bridge implementation available for download at LPCware. Just click download. You can get this information in addition to the general user manual, datasheet, design files, BSDL, PMAX2, everything you need to design with the 11U family. So here is what you need to provide. It's certified basically by the USB IF compliance shop. There are designated shops that can perform this kind of test. So you provide the checklist, it's just a long list of the features on the device and the electrical characteristic. You have to provide a test board and also firmware. These are the test result and the test ID number issued by the compliance test shop. These are some tools and utilities that allow you to put the device in various test mode. So 3 free PIDs, NXP VID. You don't need to be a USB-F member to get these WAD DPIDs, and there's no restriction on the type of devices you design. You can design any devices using the 4 transfer tabs.
Thank you very much for your time. Thanks, guys.
Thank you.